In this video, I'd like to introduce exponential notation and go over some examples outlining some of the unfortunate traps that come along with us using this really convenient notation. So, a thing that we like to do very frequently in groups, and we'll see a little bit more as to why later on, is look at taking an element and combining it with itself many times. G, and so on. Let's say, all in all, we have n copies of G. As n gets large, it can get quite cumbersome to write G, and so we wish that we had a notation that would help us to remember this. Now, our dot operation looks like multiplication, and if we were using multiplication with real numbers here, the way that we would write something like 3 times 3 times 3 times 3 times 3 with 5 copies of 3 would be 3 to the 5th. And so we are going to borrow that notation that we use with the real numbers, and we're going to use it in an arbitrary group. So if we have an element G and we would like to combine it with itself n times under the group operation that we're working with, we will abbreviate that as G to the n, just like we would in a real number system. And that's what this definition is going to be. This thing, if I have n copies of G right here, I would define this to be G to the nth power, and that will avoid a whole lot of cluttered writing. But what we need to remember about this exponential notation is that it is literally a shorthand for combine G with itself n times under whatever the group operation is. With that shorthand of exponential notation in mind, we are going to make a very important definition in abstract algebra. Let's suppose that we have an element small g inside of our group big G, and let's assume that we take G, combine it with itself under the group operation n times, and we obtain the identity. This would be a very special thing. So we are going to do this frequently inside of groups, take a group element, combine it with itself many times until we reach the identity, and that's a special occurrence. What's even more special is the first time that this happens. So let's assume that we have a group element. Let's assume that G to the nth power is equal to the identity element of that group, and that n is the smallest positive integer that has this property. Then we say that that little n, the exponent, is what's called the order of G. And I choose to write that as little o of G, where the O is standing for order, but you will see some textbooks that write it with the absolute value notation around the little element, much in the same way that we would ask for the size of the large group big G. However, this is a special property. It need not be the case that there is some positive integer n for which G to the n is equal to the identity at all. That may just never happen, and if that never happens, then we will say that an element has infinite order. So if there is some finite positive integer n for which G to the n is equal to the identity, then there is a smallest such, and that smallest such positive integer will be the order of the element G. If no such positive integer exists, the element has infinite order. Now the next thing I'd like us to do is work through an exercise where we compute some powers of elements in different groups to become comfortable with this notation and to be aware of this reminder that we have to be cautious about interpreting exponents in arbitrary groups. And I'd like us to do some examples in finding the order of an element within a group. So the two exercises I have here are to compute 3 to the 4th power in both z and z mod 5z, and then from there to discuss the order of the element 3 in both of those groups, z and z mod 5z. The second example is I'd like us to start to think about how we would generalize to this concept of negative exponents. So what do you think would be meant by 3 to the negative 2nd power inside a group like U of 10 And can we find the order of the element 3 in U of 10? So pause, see if you can write down some answers for 1 and 2, and when you've done that, unpause the video and we'll look at some solutions. First, let's take a look at that 3 to the 4th being evaluated in both z and z mod 5z. This is truly an example of why we need to be careful with exponential notation. Both the integers and the integers mod 5 are groups in an additive way. The former just purely additive, and z mod 5z under addition modulo 5. So when we write something like 3 squared, we do not mean 3 times 3, which is 9. We mean take 3 and combine it with itself for a total of 2 copies of 3 joined with the operation of the group. In the first case, when we have the integers, that answer is 6. And in the integers mod 5, we need to remember to mod the number 6 by our modulus, which is 5, and we would get a 1. In that similar way, we could compute things like 3 to the 3rd. Here, that would be 3 plus 3 plus 3, which is 9, or 4 if we're modding by 5, and 12, or 2, if we're modding by 5. So 3 to the 4th would not be something like 81. 3 to the 4th would be 3 added to itself for a total of 4 copies of 3 and an answer of 12. Now, no matter how many times we add 3 to itself, we're never going to magically get to 0 if we're working in the integers. So 3 is an example of an element in the integers with infinite order. However, in z mod 5z we see a different behavior, which is we've seen what 3 to the 1st power is, what 3 to the 2nd power is, 3 to the 3rd, and 3 to the 4th in z mod 5z, answers of 3, 1, 4, and 2. Yet when we do this one more time and compute 3 to the 5th power, that would be equal to 15 in the integers, and 15 is congruent to 0 modulo 5. 0 is our additive identity, and this is the first time we've taken a power of 3 and reached that additive identity. We conclude that 5 is the order of 3 in z mod 5z. The next question we were looking at was how to interpret negative numbers. Most often in a group, when we see a -1 in an exponent, we're not even thinking about it in this exponential notation. We view that -1 as an inverse operation within any old group. So that's the trick that we want to employ to think about things properly here. If we're looking at something like 3 to the -2 power, let's take off the negative parts of that exponent, the -1, and then let's think about what's 3 to the absolute value of that natural number. And then let's combine that with the group theoretic interpretation of a -1 sign, which is an inversion. So the way that we would want to compute something like 3 to the -2 is to first compute 3 squared and then take an inverse. Inside u of 10, we're working multiplicatively, modulo 10, so when we look at 3 squared, that's 9. And then the next part of our action is to look for the multiplicative inverse of 9. When I take 2 9s and multiply them together, I get 81, which modulo 10 is 1. That shows us that 9 is in fact its own inverse inside of u of 10, and so this 3 to the -2nd power should be interpreted as 9. If we were looking for the order of the element 3 inside u of 10, what we would do is take successive powers of 3. 3 to the 1st, 3 squared, 3 cubed, and we would continue to look for these values until we reach a value of 1, which is our identity inside u of 10. That happens for the first time when we consider 3 to the 4th power, and so inside u of 10, the order of 3 is 4. The last thing I'd like to do is leave you with yet another caution. there's another danger in using exponential notation, which is that in America we are taught a lot of different exponent rules, and we have committed them so to memory from our high school education system that they are ingrained in our brain as a universal truth. However, not all of those rules that we memorize, which are true about exponents when we're working within the real numbers, not all of those rules are true in an arbitrary group. Only some of them are, and that can be another way in which exponential notation is very difficult for us and hard for us to interpret properly. So one of the things that we'll discuss when we're next together in class is which of 4 of the most common exponent rules are true and which are not. And I'd really like us to discuss why the ones that are true remain true and the ones that are false are indeed false. Now, one thing I would suggest for you is, since you have many different examples of groups, try looking for the truth of these exponent rules in examples in very different types of groups. If they seem to always be working, that's evidence that maybe that exponent rule is universal. If you find an example of a time this equality would fail to hold for any one of these, then that would be proof that this rule is not a universal rule for all groups, and then we can start to understand why.